Scientists just discovered a planet with an atmosphere unlike anything we've ever seen. A massive interstellar object fired off a record-breaking gas jet that had people wondering if it was a spaceship. A black hole got kicked out of its own galaxy and is now tearing through space at 1,000 kilometers per second. And there's a deeply unsettling new theory, suggesting that we may only ever detect alien civilizations at the exact moment they're dying. These are not hypotheticals. These are things that happened in the last few weeks of astronomical research. And today we're going through all of them. Let's start with the one that's hardest to talk about. For over 60 years, humanity has been actively searching for extraterrestrial civilizations. 60 years of scanning the skies, listening for signals, analyzing data. And so far the result is the same. Nothing. Silence. Which brings us right back to Enrico Fermi's famous question. If intelligent civilizations exist out there, where is everybody? A researcher at Columbia University in New York named David Kipping recently proposed an answer to that question, and it's not a comfortable one. His argument goes like this. Whenever we search for any class of objects in the universe, the first ones we find are always the outliers, the weird ones, the extreme cases, the ones that scream the loudest. This is a pattern that repeats everywhere in astronomy. The very first exoplanet ever discovered wasn't orbiting a normal star. It was found near a radio pulsar, a rapidly spinning neutron star left behind after a supernova explosion. Nobody expected to find planets there. Since then, we've discovered nearly 8,000 exoplanets around ordinary stars, but only about a dozen around pulsars. That first discovery was a statistical freak. When we found the first exoplanet around a Sun-like star in 1995, it was a hot Jupiter, a massive gas giant orbiting absurdly close to its parent star. Hot Jupiters turned out to be extremely rare. Most giant planets orbit far from their stars, just like Jupiter does in our solar system. But the hot one was easier to detect because it tugged on its star so violently, so that's what we found first. Another outlier. Look at the night sky with your naked eyes. About a third of the visible stars are giants, enormous luminous beacons, but giants are actually incredibly rare among stars. The overwhelming majority are dim red dwarfs that you can't see without a telescope. The giants are just so bright that they dominate your view. And supernovae. A massive star might explode as a supernova maybe once or twice per century in any given large galaxy, yet we discover over 1,000 supernovae every year. Why? Because each explosion is so spectacularly bright that modern robotic telescopes can spot them across enormous distances. The pattern is clear. In any population of objects, we detect the extreme events first. The rare, loud, dramatic ones that stand out against the background. Now apply that logic to the search for extraterrestrial intelligence. If this pattern holds, and there's no reason to think it wouldn't, then the first alien civilization we detect will not be a quiet, stable society going about its business. It will be a civilization experiencing something extreme, something dramatic, something loud, like dying. Think about it. A civilization reaches its technological peak. It starts broadcasting powerful radio signals into space. It fires laser pulses across interstellar distances. It develops nuclear energy. And right around the same time, it starts running out of resources. Wars begin over what's left, and the weapons available are now nuclear. You can see where this is going. From the outside, from hundreds or thousands of light years away, this would look like a sudden burst of detectability. A brief, bright flash of technological activity, radio emissions, atmospheric pollution with unusual chemical signatures, maybe even the infrared glow of nuclear detonations, followed by silence. A deathbed signal. It's grim, it's uncomfortable. But it follows directly from how detection bias works in astronomy. The most visible moment in a civilization's existence might be its last. So how do you search for something like that? Traditional methods won't work well. Pointing a radio telescope at individual sun-like stars and listening patiently is fine if you're looking for a long-lived, stable signal. But a death flash would be brief and unpredictable. It could come from any direction at any time. If you're looking at the wrong star when it happens, you miss it entirely. What you need is an all-sky monitor, something that watches everywhere simultaneously and waits for a short, powerful, anomalous burst that stands out from the background noise of the universe. This is exactly the strategy being pursued right now near Lake Baikal in Russia, in the Tunka Valley. A team from Moscow University has been running a detector array originally built to catch cosmic rays, high-energy protons slamming into Earth's atmosphere and producing brief flashes of Cherenkov radiation. But the same equipment can detect short laser pulses arriving from deep space. The key advantage is that it can distinguish between the two. A signal from an astronomical distance arrives with a flat wavefront. The light has traveled so far that the curvature of the original spherical wave has flattened out to essentially a plane. A Cherenkov flash from Earth's atmosphere arrives with a noticeably curved wavefront because the source is close. The detectors can easily tell them apart. This search has been running for 4 years now, and there are already some interesting preliminary results. Whether they'll lead to anything definitive remains to be seen. But the approach itself represents a fundamentally different way of thinking about the search for extraterrestrial intelligence, not listening for a conversation, but watching for a catastrophe. Now let's talk about our interstellar visitor. The object designated 3I Atlas has been making headlines for months. It's the third known interstellar object to pass through our solar system, a body that originated somewhere else in the galaxy and is just passing through, never to return. And for a while, some people were genuinely asking whether it might be an alien spacecraft. It's not. 3I Atlas is a comet, a natural body made of ice and rock, evaporating as it approaches the sun and producing a visible gas cloud and tail. We've been tracking it since it crossed Jupiter's orbit, and every piece of data confirms that it's a perfectly natural, if extraordinary, cosmic visitor. Its chemical composition is slightly unusual. More carbon dioxide and less water vapor than most comets in our solar system, but not unprecedented. Some of our own solar system comets show similar ratios. Traces of iron and nickel atoms have been detected in the outgassing, which is also uncommon but not unique. No aliens required. The most interesting feature has been its anti-tail, a stream of gas pointing roughly toward the sun rather than away from it. Anti-tails happen when a comet ejects material in a specific direction, and the geometry of the orbit makes that jet appear to point sunward from our perspective. This has been observed before in other comets, including the second interstellar object, Comet Borisov, discovered in 2019. What made people nervous about 3I Atlas was that this anti-tail persisted for an unusually long time, nearly a month, and maintained a remarkably stable direction. If the comet were a spinning body with a single active vent, you'd expect the jet to trace out a spiral as the comet rotated. Instead, it barely moved. This is what fueled the spaceship speculation, a constant thrust in one direction. That sounds like an engine, but astronomers at the TD Observatory on Tenerife in the Canary Islands watched the anti-tail carefully over many days and found that it does change direction very slightly with a period of about 16 hours. And the comet itself rotates with a period of about 16 hours. This means the vent is located very close to the comet's rotational pole. The body spins, but the jet barely moves because the nozzle is almost exactly on the axis of rotation. A slight offset from the pole produces the small wobble they observed. Mystery solved. Not a spacecraft. Just a beautifully behaved natural object with a conveniently placed vent. We'll continue observing it for several more months before it accelerates out of the solar system forever. No rocket we currently have can catch it. So whatever data we collect now is all we'll ever get from this particular interstellar guest. Now for the discovery that genuinely stunned the astronomical community. The James Webb Space Telescope has been operating for 4 years now, and in that time it has delivered breakthrough after breakthrough across every branch of astronomy. But this particular finding might be one of its strangest. Webb pointed at a planet orbiting a radio pulsar, the millisecond pulsar designated PSRB 2322-2650. This planet was first detected in 2017 through tiny variations in the timing of the pulsar's radio pulses caused by the gravitational tug of the orbiting body. But nobody had been able to study the planet itself in detail because, well, it's orbiting a dead star and is incredibly faint. But here's the thing about planets around neutron stars. They're actually easier to study in some ways than planets around normal stars. There's no blinding glare from a luminous host star washing out the planet's own feeble light. A neutron star is brilliant in radio and X-ray wavelengths, but in the optical and infrared, it's almost invisible. The planet can actually outshine its parent star in infrared light. So Webb captured the infrared spectrum of this planet's atmosphere. And what it found makes no sense. The atmosphere is dominated by carbon, not carbon dioxide, not carbon monoxide, pure molecular carbon, C2 and C3 molecules. And there's essentially no oxygen and no nitrogen. This is bizarre for a very specific reason. Carbon is extraordinarily reactive with oxygen, especially at high temperatures. And this planet is hot, extremely hot. It orbits roughly 100 times closer to its pulsar than Earth orbits the Sun. The day-side temperature exceeds 2000 degrees Celsius. The night side is cooler, but still around 600 degrees, roughly the temperature inside a kiln. At those temperatures, if there were any oxygen present, the carbon would have combined with it instantly to form carbon dioxide or carbon monoxide. The fact that free molecular carbon exists in this atmosphere means there is genuinely no oxygen available to react with, and no nitrogen either, because carbon-nitrogen compounds would have formed just as readily. So where did this atmosphere come from? One theory is that this planet is actually the stripped core of a companion star that was consumed by the pulsar. In binary star systems, when one star becomes a neutron star, it can gradually strip material from its companion through gravitational interaction, heating it, evaporating its outer layers, eventually leaving nothing but the dense core. Astronomers sometimes call these systems black widows, named after the spiders where the female devours her mate. But stellar evolution models predict that the core of a stripped star should contain a mix of carbon, oxygen, and nitrogen, the products of nuclear fusion reactions that occur in stellar interiors. A pure carbon core shouldn't exist. The nuclear reactions that produce carbon also produce oxygen and nitrogen as byproducts. Every stripped stellar core we've ever observed contains all three elements. Yet here we have what appears to be a nearly pure carbon body. The astrophysicists studying this object are genuinely baffled. No existing model of stellar evolution or planet formation predicts an atmosphere like this. And there's another anomaly. Every other planet ever found around a neutron star has been extremely dense, tens of grams per cubic centimeter. The intense radiation and gravitational field of the pulsar strips away any lightweight material, leaving only the heaviest, most tightly bound elements. But this planet has a density of less than 2 grams per cubic centimeter, similar to Jupiter. Somehow it retained its lighter layers despite being blasted by a pulsar at close range. The planet's shape is also extraordinary. The intense gravitational field of the nearby pulsar has deformed it into an elongated ellipsoid, not quite egg-shaped, more like a pear. One end is more pointed, stretched toward the pulsar by tidal forces, while the other end remains more rounded. This is the kind of distortion you normally see in stars that are being gravitationally consumed by a companion, not in planets. And here's the detail that captures everyone's imagination. At the extreme pressures deep within this carbon-dominated atmosphere, the carbon would undergo a phase transition. It would crystallize into diamond. This planet almost certainly experiences diamond rain, carbon particles forming in the upper atmosphere, crystallizing under pressure as they sink deeper and falling like precipitation toward the core. A steady downpour of diamonds sinking through a superheated carbon atmosphere on a pear-shaped world orbiting the spinning corpse of a dead star. It's one of the most alien environments ever confirmed by direct observation. And before anyone gets excited, no, we cannot go there and collect the diamonds. The planet is far too distant and far too hostile for any conceivable mission. Moving on to Titan, Saturn's largest moon and one of the most fascinating worlds in the solar system. Titan is remarkable. It's nearly twice the size of our moon. It has a thick nitrogen atmosphere, the only moon in the solar system with a substantial atmosphere. It has seas and lakes on its surface. Rivers flow across its landscape. Clouds drift through its sky, and rain falls from them. Of course, everything on Titan runs on a different chemistry than Earth. The temperature is minus 180 degrees Celsius. Water exists only as rock-hard ice. The liquid that fills Titan's seas flows in its rivers and falls as rain is methane, natural gas in liquid form. For years, scientists believed that beneath Titan's icy crust, tens of kilometers below the surface, there existed a global ocean of liquid water. The reasoning was straightforward. Planetary interiors are warmer than their surfaces. Heat is generated internally through radioactive decay and retained from the body's original formation. And in the case of moons orbiting giant planets, tidal forces from the parent planet can flex and squeeze the moon's interior, generating additional heat through friction. We see this clearly with Jupiter's moons. Europa has a subsurface ocean beneath its ice shell. Io has active volcanoes driven by extreme tidal heating. Saturn's moon Enceladus shoots geysers of water into space from an underground sea. So the expectation was that Titan, being large and subject to Saturn's gravitational influence, would also harbor a deep global ocean beneath its surface. Models predicted this ocean could be hundreds of kilometers deep, and where there's liquid water and energy, there's the possibility of life. But new analysis of data from the Cassini spacecraft, which spent 13 years studying the Saturn system before its dramatic plunge into the planet in 2017, has complicated this picture. Cassini made multiple flybys of Titan, and each pass allowed scientists to map the moon's internal gravity field by tracking how the spacecraft's trajectory was deflected. When researchers recently reanalyzed this gravitational data with improved models, they found that the evidence no longer supports a single global ocean. Instead, the data is more consistent with multiple separate bodies of liquid water beneath the surface, enormous subsurface lakes or seas, rather than one continuous ocean. This doesn't diminish the possibility of life on Titan. Whether the water exists as one global ocean or many separate reservoirs, the conditions for potential biology remain the same. And Titan has a unique advantage for astrobiology that no other world can match. On Earth, life emerged approximately 4.5 billion years ago. Whatever chemical processes gave rise to the first living organisms happened so long ago that virtually no trace of them remains. We can only theorize about how life on Earth began. The evidence has been erased by billions of years of geological and biological activity. On Titan, the extreme cold means that all chemical reactions, including biochemical ones, proceed at a glacial pace. If life is emerging on Titan, it would be in the earliest possible stages, the very first steps of the process. We might be able to observe the chemistry of life's origin in real time, preserved by the deep freeze, like a biological snapshot of what Earth itself went through billions of years ago. And it's worth noting that the pressure at tens of kilometers depth on Titan is not as extreme as you might think. Titan's surface gravity is only about 1/7 of Earth's, and the density of the material above is lower. A depth of several tens of kilometers on Titan corresponds to a pressure roughly equivalent to a few kilometers of ocean depth on Earth. We know life thrives at those pressures. The bottom of the Mariana Trench is teeming with organisms. In 2028, NASA plans to launch the Dragonfly mission, a nuclear-powered rotorcraft that will fly through Titan's thick atmosphere like a drone, landing at multiple sites across the moon's surface. It will carry a portable biochemistry laboratory. The hope is that it will find the first evidence of prebiotic chemistry, or possibly even primitive life itself, on a world that seems frozen in time. And finally, something truly spectacular. It appears that astronomers have caught a supermassive black hole in the act of escaping from its own galaxy. Here's the background. Most large galaxies have a supermassive black hole at their center. We're fairly confident about this now, and galaxies frequently merge with each other. When two galaxies collide and combine, their central black holes both end up in the merged galaxy. Sometimes 3 galaxies merge, leaving 3 supermassive black holes in a single system. These black holes are massive enough that their orbital motion through the galaxy is gradually slowed by gravitational friction with surrounding stars. Over time, they sink toward the center of the merged galaxy, and then things get interesting. If two black holes spiral together, they can merge. We've detected the gravitational waves from such events multiple times since 2015. But the gravitational waves from a merger don't always radiate symmetrically. If more energy is emitted in one direction than another, the resulting merged black hole gets a gravitational kick, a recoil that can be powerful enough to send it flying out of the galactic center entirely. And if three black holes end up in the same galactic core, the three-body problem takes over. Three gravitationally bound objects cannot maintain stable orbits around each other indefinitely. Inevitably, two of them form a tighter pair and eject the third at high velocity. This is fundamental orbital mechanics, the same physics that governs the chaotic dynamics in Liu Cixin's famous novel. In 2023, astronomers examining images from the Hubble Space Telescope noticed a thin, bright streak extending from the center of a galaxy catalogued as RCP-28. It looked like something massive had punched through the galaxy's body and left a luminous trail behind it. The James Webb Space Telescope was brought in to investigate. It captured the spectrum of this bright feature, and the results were striking. A massive object, almost certainly a supermassive black hole, has indeed been ejected from the galaxy's core. It tore through the main body of the galaxy and is now plowing through the diffuse gas in the galaxy's outer regions at roughly 1,000 kilometers per second. As it moves, it drives a shock wave through the surrounding interstellar gas. The shock heats the gas to extreme temperatures, causing it to glow brightly. What we see from Earth is essentially the wake of this runaway black hole, a luminous trail of superheated ionized gas marking its path through the galaxy. Mathematical models confirm that an object moving at this speed through gas of this density would produce exactly the kind of shock structure observed. The physics checks out perfectly. But there's a subtlety that makes this even more interesting. The black hole itself is tiny in terms of physical cross-section. Its event horizon, even for a supermassive black hole, is minuscule compared to the scale of a galaxy. So it's not the black hole itself that's plowing through the gas like a bullet, it's the entourage it brought with it. When a supermassive black hole is ejected from a galactic center, it doesn't leave alone. The gravitational well around it is so deep that nearby stars cannot escape. They get dragged along, a small but dense cluster of stars, gravitationally bound to the fleeing black hole. As these stars age over millions of years, some evolve into red giants and shed their outer layers, releasing gas that feeds the black hole's accretion disk. This disk, combined with the gravitational influence on surrounding gas, creates a much larger effective cross-section as the whole system barrels through the galaxy's outskirts. The black hole has been flying for an estimated 10 million years since its ejection. That's long enough for the original accretion disk it carried from the galactic center to have been consumed. But the captured stellar cluster keeps replenishing the gas supply, maintaining the black hole's visible impact on its surroundings even millions of years after the initial ejection event. We're watching a supermassive black hole, an object with the mass of millions of suns, hurtling through a galaxy at 1,000 kilometers per second, dragging a retinue of captured stars behind it, plowing through interstellar gas, and leaving a glowing scar across the face of its former home. And the truly remarkable thing is that this was predicted decades ago. The physics of gravitational recoil from asymmetric mergers and three-body ejection has been understood theoretically for a long time. But seeing it actually happen, watching the luminous trail of a runaway black hole stretched across a distant galaxy, is something else entirely. It's one of those moments where the universe takes a theoretical prediction and makes it viscerally, visually real. These are the kinds of discoveries being made right now, in real time, by instruments like the James Webb Space Telescope and ground-based observatories around the world. A planet that rains diamonds orbiting the corpse of a dead star. A moon where the chemistry of life's origin might be playing out in slow motion. A black hole that got kicked out of its own galaxy and is now screaming through space at unimaginable speed. And the haunting possibility that when we finally detect another civilization, the signal we receive will be their last. Every week brings something new, something stranger than the last, And the picture of the universe that's emerging from all of this data is more complex, more violent, more beautiful, and more unsettling than anything we imagined even a decade ago. We are living through the golden age of discovery. And it's only just beginning.